Now see, we already discussed about the concept of work done. We discussed this thing, work done W, that is equal to force into displacement. Here in this particular definition, when we take force into displacement, so at that time we consider force as a constant quantity. But it is not necessarily always the force acting on the object or the particle that remains constant one. If the force is continuously changing one, then how to calculate the work done? So now the next topic, that is work done by a variable force, right? So first here we will discuss the concept of work done by a variable force, that is with the help of graphical method, right? See how we carry out this thing. So first we have to draw a graph of force versus displacement. And suppose here force is in one dimension only, right? For simplicity we consider it. And the graph of force versus displacement, that is as shown in the figure. And suppose under the effect of this variable force, this force is a function of displacement. As displacement of the particle changes, the force acting on it, that is changing one. So under the effect of this variable force, suppose the particle moves from initial position xi to final position xf. Now we want to calculate the work done during this displacement. Okay. So here what we have to do, here we have to divide this area under the graph with respect to displacement axis into so many infinitesimal thin stripes as shown in the figure. Suppose we consider one such strip, which one is dark here, then if we take area of this strip, then see here. So this particular portion, height of the strip, that will give you the force, and on x-axis this particular width of the strip, that is suppose delta x. So this is the force into delta x. So actually that is height into width. So that is the area of the strip. That is the area of the strip. So here in this particular case we can say this area, that is actually nothing but force into displacement, and that is equal to work done. But here see, you think like this much small area, that is out of the strip, which one is under the graph, and that is not under the consideration. But here I mentioned earlier, we have to consider this particular strip very thin in the width. So this particular upper part, that will be almost neglecting one. So in that particular case, for this displacement delta x, which is very small, we can consider this force as constant quantity. And when for delta x displacement force is constant, directly you can write delta w, that is f delta x. In this way, suppose starting from initial position to final position, we consider so many infinitesimal small displacements, delta x1, delta x2, delta x3, delta x4, like that. And for each small displacement, suppose the constant forces are F1, F2, F3 respectively, then we can write the work done for first delta x1 displacement, that is delta w1 equal to F1 delta x1. Then for second one delta w2, that is F2 delta x2. up to n part, we can write delta Wn, that is Fn delta Xn. Then if we take the summation of all these work done, then we will get the total work done, and actually the total work done will be the total area under the graph. Clear? So we can write the total work done, that is delta W1 plus delta W2 plus delta W3 up to delta Wn. So W, that is sigma xi to xf. We have to take this number of strips between xi to xf. So we have to take this type of summation between these two limits. Okay, this is the lower limit, this is upper limit. So that is f, which is a function of x. So fx into delta x, right? But here if we take this delta x infinitesimal small means tends to 0. Limit tends to 0. In the concept of differentiation we discussed this thing, right? So if we take here this delta x very small, right? Then we can write the total work done W, that is limit delta x tends to 0, sigma xi to xf, fx delta x. And this is nothing but the total work done, and which is the entire area under the graph with respect to displacement axis. But now see, this particular concept of the calculation of work done, that is tedious one. This is not easy thing. So here we have to take help of mathematics. In mathematics, there is a such concept for function and variable, and this type of problem is solved in mathematics with the help of integration. So this one can be represented as integration xi to xf f dx. So here we have to carry out the integration of varying function f with respect to the variable dx, starting from lower limit xi to upper limit xf. And this particular symbol that represent integrate this one. So integrate force with respect to displacement. But now the question is this one, how to carry out this displacement, right? So we can write this W like this also. So W, that is integration R1 to R2 vector f dot vector dr. So in broad sense we can write this equation like this. So for varying force, the work done can be expressed as a definite integral of force over displacement. Definite integral means you have to carry out the integration between these two limits. This is the lower limit, this is the upper limit. So it is called the definite integral. But now the question is this one, how to carry out the integration. So just like differentiation, we studied in differentiation. Suppose we have a function x raised to n, and if we take d by dx of x raised to n, then directly we have the formula, that is nx raised to n minus 1. Exactly like that here, integration of x raised to n dx, we have the formula that is equal to x raised to n plus 1 upon n plus 1. So that our entire summation, that is this one actually. Clear? So this is the formula for integration. Some integrations in text given to you for cos theta, sin theta, tan theta, 1 upon x, like that. Just you have to remember those integrations, right? How this equation comes for integration, that is none of our business. Directly we have to use these equations. Clear? Now here see, like square and square root. Suppose we take square of x, then your answer is x square. Then if you take square root of x square, then you will get again x. So we can say square and square root, that is opposite processes. Like that, integration and differentiation are also opposite processes. See here, integrate x raised to n with respect to dx. So integration is carried out, so then after no need to represent this symbol. Be careful. When you write under root x square, then your answer is x. Then never use root, because this root represents this thing. Take the square root of x square and this one is the final answer. Like that, this symbol of integration, that is one type of operator. Clear? So now the process is carried out. Your answer is x raised to n plus 1 upon n plus 1. So no need to place that symbol. Be careful here. Now this is your answer. If you take differentiation of this answer, okay? So d by dx of x raised to n plus 1 upon n plus 1. So in differentiation what we do? We take power in multiplication and power will be decreased by 1. So this power n plus 1, that is taken in multiplication. Then x raised to n plus 1, that is the power, and now minus 1, so it is decreased by 1. Denominator, that is as it is, n plus 1 cancelled. Here 1 cancelled. So your answer is x raised to n. So first if you integrate x raised to n, and then after if you take differentiation of the answer, you will get again the function itself. Similarly, first if you carry out the differentiation of x raised to n, d by dx of x raised to n, so your answer is nx raised to n minus 1. Now take integration of this one. So integration of nx raised to n minus 1 dx. N is constant, keep it as it is. Now power will be increased by 1, and then after divide whole thing by power. So x raised to n minus 1 plus 1. So power is increased by 1. Then divide by the power that is n minus 1 plus 1. 1 cancel. This n will be also cancelled, and your answer will be again x raised to n. So here see, mathematically how to carry out differentiation and integration, that we discussed. But now here again let's discuss this thing, the physical interpretation of this one, right? In differentiation actually what we do, so in differentiation we think about the phenomenon which take place over the large scale, right? Then after, by taking smaller and smaller time interval, so we can say if the phenomenon takes place over the large scale, then with the help of differentiation we explain that phenomenon over infinitesimal small scale. That is the use of differentiation in physics. Then integration. So in integration what we do? We consider the phenomenon which takes place over infinitesimal small scale. Then after we add up all such phenomena which takes place over small scale, and finally with the help of integration we explain that phenomenon over the large scale. So this is the concept behind these mathematical formulas. Clear to all of you?